Hello mathematicians, thank you for joining me. Today what we're going to be doing is we're going to be working through the theorem, suppose that A is a square matrix. If A is nilpotent, then it is singular. And so we'll want to be able to provide a proof of this theorem. Before we get into the actual proof, what we want to do is determine what's going on. So we're going to actually make a table of things that are given to us and things that we have to show. And so what's given to us in this case is that it is a nilpotent matrix, and what we have to show is that it is a singular matrix. So what we want to do is write down things that are equivalent to this, or that this implies, and things that this is equivalent to, or that imply this, so that somehow we can then connect these to get a complete proof. So if we start with nilpotent, what does that mean? Well, matrix is nilpotent if a to the k is equal to 0 for some natural number k. That is, if I multiply a by itself again and again and again, eventually I'll get out the 0 matrix. So not the number 0, but the 0 matrix. Now, if we want to show that it's singular, we said that a matrix was singular if the determinant of A was equal to 0. So somehow we want to show that the determinant of A is equal to 0 if A to the k is equal to the 0 matrix. Now, what else can we derive from here is notice that, well, if a to the k is equal to 0, this implies that the determinant of a to the k is equal to the determinant of the 0 matrix. But what is the determinant of the 0 matrix? Well, it has all entries 0. So if we calculate that one out, we would just say that that determinant will indeed just be 0. So we do know that a to the k, the determinant of a to the k, is indeed equal to 0. So how can we get from here to here? Well, what we have to think about are some properties of determinants. In particular, what I have to do is I have to recall that the determinant of A times B is equal to the determinant of A times the determinant of B. Now, how I'm going to use that is notice that what I have here is A times A times A times A times A. So if I let A to be A and B be B to the k minus 1, what I get is the determinant of A to the k is the determinant of A times the determinant of A to the k minus 1. I can use that again to get A times A times A to the k minus 2. And in the end, what I get is, this is the same thing as saying, since this is equal to 0, this is actually equal to the determinant of A to the k. So what I get is the determinant of A to the k is the same as the determinant of A to the k, which is the determinant of 0, which is 0. So now I have to use this in order to get this out. So how am I going to do that? Well, notice that in this case, we have matrix times itself in getting out the 0 matrix. We can have matrices that are non-zero that end up being the 0 matrix when we raise them to powers. For example, if I have 1, 0, 0, 0, if I square that matrix, I do indeed get 0, 0, 0, 0. So I have a non-zero matrix squared is equal to the 0 matrix. However, with real numbers, can I have a number multiplied by itself, ended up being 0? Well, what we know for real numbers is that if A times B is equal to 0, then A equals 0 or B equals 0. Since the determinant is a real number, what this means is that, well, one of these terms in here multiplied together, they all multiply out to be 0, so one of the terms has to be 0. But each of these terms are A, so what that implies is precisely that. The determinant of A has to be 0, because if I multiply it together a bunch of times, I get out 0, one of the terms has to be 0, but all the terms are the determinant of A, hence the determinant of A is 0, so we have a singular matrix. So now if we combine together what we said before is, let A be a squared nilpotent matrix, then we have that. That means that A to the k is equal to 0. Therefore, we know that, well, the determinant of A to the k is the same as the determinant of A to the k. Since A to the k is 0, then the determinant of the 0 matrix is just 0, so the determinant of A to the k is 0. But the determinant of A is a real number, so a real number to a power is 0 implies that the real number is 0. Therefore, by definition, our matrix is singular because its determinant is 0. Thank you for watching. As always, I hope you learned something today, and I hope you enjoyed the process along the way. If you did, make sure to like the video and subscribe to the channel. It helps me to know which videos are helpful, and it helps other people to find these videos so that they can also get help. Thank you.